Patrick, 1 hour, 25 minutes.
Sure. Thank you, Pinaki. Thank you, the organizers, for inviting me, for allowing me the chance to talk to you. It's a real, it's an honor and a privilege to get to teach. Oh, sure, you're here. It's very nice. Took about half an hour, but we did it. Okay. So you're hearing a lot about glasses this week, right? As you might have noticed. Good news, we sort of know each other, so we coordinated. So we're trying not to overlap too much, but there's a healthy amount of overlap to help you make connections between different concepts. That said, if something's unclear, I have no personal agenda with those lectures, right? There's no final exam. I don't get evaluated on whether I covered enough material. So I've prepared some material. I hope I have enough to cover all my time, but if I don't go through it, it's really not the end of the world. What's really most important is for you to get to learn what I can get to share with you if there's anything that interests you. And if I don't know it, I'll just tell you so, and we'll move on to something else. So don't hesitate. I'm going to be talking about the glass problem and the glass problems, or the glass problem. And really, I don't need to give another introduction to glasses, but I can't imagine not giving one, because we all have a slight different bias into how we think about this particular family of problems. So I'll give you an introduction that you probably know everything about already, but it'll give you my angle, at least, on how I think about what's going on. And I think it's going to help frame the rest of the lectures as well. So I sort of provocatively added an S at the end of problem, because I like to think of the glass problems and coming from different viewpoints themselves, right, on glasses. So if you're a material scientist, you care about glasses and materials. You want to find a way to make better glasses, or make glasses. Let's say sometimes that's even the only requirement for some materials. So the general recipe for making a glass, right, is you start from a high temperature liquid and you cool it. Right, that's the very basic recipe. As you cool it, you can be monitoring some quantities like the enthalpy or the specific volume, say. So let's say the specific volume as you cool the liquid will typically go down. And this being a liquid, it often has, or typically has, a first order phase transition to a crystal, right? Which means that the thermodynamic preferred ground state below a certain temperature, below the melting temperature, would be a crystal. So it would form. But that would sort of defeat the purpose of a material scientist trying to form a glass, because when you're trying to get a glass, you're trying to make sure your system actually does not crystallize and will remain what's called then a supercooled liquid, and then depending on how you cool this, you'll get glasses of different properties. It falls out of equilibrium and becomes non-ergodic in a myriad of different ways. And so if you're a material scientist, often when you think about the glass problem is just how do you get the material, right? So if you're trying to get metallic alloys to form glasses, right, you have to figure out the right compositions, the right cooling protocols such that you will get a glass at the end. If you're a chemical physicist, you think of the glass problem in a slightly different lens, right? You say, okay, assume that I have a material scientist friend who got me a glass, or a good glass former. I'm particularly fascinated by how the viscosity, say, will increase as I lower temperature. All right, so what's remarkable is twofold. The first one is that it looks like nothing changes in the structure while the viscosity shoots up dramatically. That's what we call the glass transition. So it looks like a liquid, but yet it feels like a solid. You have a material at the end. and if you cool water through 0 Celsius, it also changes dramatically in viscosity over a very short temperature range. This is a dramatic change in the ordering of the molecules that form water, right? So you're not so surprised to know that ice has different materials properties than water above 0 Celsius. But what's really strange about glasses or puzzling about glasses, at least in the eyes of a chemical physicist, is that it is a solid without any obvious order developing. right? So that's part one. And then the second one, also Sri mentioned, is that when you cool your system, there's different sort of universality ranges within the glass formers. You have some glass formers that just behave erroneously, right? So you have less kinetic energy, so you go slower because there's barriers to surmount. But there's a variety of different glasses that are called fragile, right, just by definition, where they have what's called a super Arrhenius relaxation. Meaning that as you lower temperature, not only do you have some barriers of unknown origin you need to surmount, but those barriers themselves grow. Right? And again, still with little apparent change. Right? So that's quite a puzzling aspect of glass formation. And then if you're a low temperature physicist, you may have friends who are material scientists who gave the materials to your chemical physicist, and then they cool it down up until it's rock solid, and the chemical physicist doesn't know what to do with it, so they just pass it on to you as a low temperature physicist. And then glasses are very anomalous materials, right? And by anomalous, I just mean that if you open your classic solid state physics textbook and you look at what a solid property should be, and you then go measure the same properties in the glass, there's a mismatch. Right, then the origin of the mismatch at the superficial level is pretty simple, right? Most of those properties calculated in solid-state physics textbooks are for crystals, and you have something that is non-crystalline, right? But because the microscopic origin of those effects is not so well understood, we call them anomalous. And that includes transport properties, that includes density of vibration excitations. Another nice way in which one can think about low temperature properties is to think about systems that truly have no temperature, right? Collections of grains in particular. So this is an example of a configuration of grains. You can barely see the grains there. So here's one grain on this slide that are jammed together. This is what it's called. They're jammed together. And this is an image from the late Bob Behringer's lab. And what he figured out is a way to image forces propagating through those systems. And what you can see is that the force distribution and the way force propagates seems to have very little to do with the actual structure of the amorphous solid that underlies it. Right? You have some really strong forces in parts. You have some spots that have almost no forces. And looking at them graphically, it's not clear why, at least superficially, why one region is one and the other one is the other. And there was a proposal now 20 years ago by Sid Nagel and Andrea Liu to try to unify those two sets of properties. Right? To say, well, if I have a low temperature jammed solid, or a granular jammed solid like sand, right? Or those nice photoelastic disks, or if I have a low temperature glasses, maybe I'm relooking at the same material, right? Or maybe they're materials with the same similar properties. And they drew some sort of phase diagram that would suggest a unification between all of those. But this was a proposal. This was an idea put forward, and it launched a pretty significant program, both experimentally and theoretically, in trying to reconcile jamming with some properties of the low temperature classes. We're physicists, or at least we like to think. Well, I'm a chemist actually, but I like to think I'm a physicist. So if we want to be trying to study all those different problems, we try to simplify it in as simple as a model as we can imagine that could recover all three families of problems into one. And in the case of this particular lecture, is going to be hard spheres. Right? This is a school in entropy. Turns out hard spheres only have entropy. Right? There's no energy involved, so it's all an entropic system. So I thought it was very thematically correct. It also happens to be my favorite model, so it was a good match of interest and thematic. All right, so why do I say a hard sphere system recovers or can treat the three different problems that I lumped into the glass problems family? Well, here's the following explanation. Right, so hard sphere systems are what we say athermal or temperature independent, because the partition function only depends trivially on temperature. So you can rescale pressure here by temperature, and you're done with roll temperature. So the only really equilibrium tuning parameter you have is the packing fraction, or the volume fraction or the density, if you prefer, of those hard spheres. And so if you start from a very low density set of hard spheres, you have something that behaves essentially like an ideal gas. And as you crank up the density up to about 50% packing fraction, you get a spontaneous transition, as Francesco described yesterday, Professor Sciortino described yesterday. And they order in FCC or HCP or different variants of the close pack solid. Actually, it turns out that free energy difference between the different crystals is very, very minute at melting. So, and then if you keep on cranking up the pressure, so if you keep increasing the packing fraction, the pressure cranks up and eventually diverges, right? And when does it diverge? It diverges when the particles are mechanically touching one another, right? Corresponds to collisions happening every instant, and thus the divergence in pressure. The exchange of momentum is maximal. Okay, so that's what a material scientist does not want to have, right? You don't want to go on this spontaneous thermodynamic branch. So what you want to do is to supersaturate or obtain generically a supercooled liquid along this branch here. And as that system gets denser and denser, one thing you can look at is a quantity that Francesco was looking at this morning. So we called it D. In some of his lecture notes, he called it delta. So in this case, it's called delta of T as a function of temperature. But this is the mean square displacement, the exact same quantity he was looking at. All right, so if you're looking at low packing fractions, at very, very short times, the system behaves ballistically. Right? Before you collide with any neighbor, you're just going in straight line. There's no force exerted on you because it's a pure contact interaction. Right? And if you wait a long time, then you diffuse away. Right? So you go like T squared short times if you have a Newtonian dynamics, and you go like T at a long time as you're diffusing. And as you increase the packing fraction, what happens is that a sphere will spend more and more time, if you want, colliding with its neighbors, going back and forth. So you'll have the emergence of a caging plateau before it can finally find a way to move out. So you always at long times get a diffusion, diffusivity, a finite diffusivity, but it gets to be smaller and smaller as this caging regime becomes longer and longer. Very much consistent with what Francesco was describing this morning. At some point, those simulations become so long, you run out of patience, right? You get bored. So the plateau will be longer than you can be bothered to look at your simulations for. So you'll say, well, this is a glass, clearly, because it's not diffusing anymore, it's not relaxing. Right? And to a large extent, the experimental definition of a glass is just that. Right? Once your experimental colleagues or your experimentalists run out of patience, you say it's a glass. And then you can make building materials with it if you really, if it's more than just the 5 years of your PhD. It's more like the millions of years or billions of years or hundreds of billions of years that this building will stand that matters. So, okay, so that's what That's what happened on this branch here. And when you run out of patience, then you stop relaxing. But there's still volume. There's still space between particles. So you can keep on cranking up the pressure. You can keep on cranking up the pressure, and it shoots up. And it only really diverges when particles, again, become mechanically in contact. And what do you have then? You have an amorphous solid that is mechanically robust. Right? You have a jammed configuration. And depending on how impatient or patient you were to wait along this branch, you will get different jammed configurations. Right? But they all have very similar properties. So that's the minimal model we're going to be looking at for the rest of those lectures. There's not going to be any temperature other than in rescaling pressure, and all is going to be controlled by the packing fraction. Now, Sri sort of, and we're going to be looking at, and I should say we're going to be looking at the at least two of those two problems, right? First, how can you get something that does not crystallize, and then how does it get slow and follow the equilibrium? And we may or may not talk about jamming, depending on whether you have better questions to discuss. Okay. Now, you all saw Sri's lectures on Monday. I was there for half of them, so I have a feeling with what was said. And one message, sort of a meta message that you might want to be taking from those lectures, that it looks like it's very complicated to try to describe classes. Right? And this is a newspaper articles from 10 years ago, when you were in primary school, I guess, where they were discussing the state of the glass problem 10 years ago. eons ago and on many scales. And there was a pretty famous experimental physicist at Harvard called Dave Waits who was interviewed, and he said there are more theories of glass transition than there are theorists who propose them, right? Which was rough, which actually he's still an outstanding, we can edit the video, right? But he was on my thesis committee, so that was fair. And Dave Waits is really an amazing experimental physicist, and this is experiments that he was running at the time. They were colloidal suspensions of essentially rough, hard sphere-like particles, and he managed to image them in 3D and with time. So they were getting essentially colloidal simulations of what an amorphous solid would be. And so this beautiful. But we said this in part. There were a lot of glass theories, and in part to pick at his theory colleagues for such a mess. And the first response you might have when you hear this comment as a theorist or a senior-gen person is that, well, Dave Waits is not a nice person, right? Maybe he was not a nice person back then. And then because he's sort of picking on people and fields, and then if you take a step back, actually, that when I heard this the first time, it reminded me of a book that I'd read shortly before that, by Thomas Kuhn, called The Structure of Scientific Revolutions. Thomas Kuhn is considered one of the sort of modern philosopher of science. He wrote this book as a pretty young, I think he was an assistant professor at the time. Anyways, about how conceptual changes take place in science, right? How scientific revolutions take place. And in that book, he was describing the state of 18th century chemistry of oxidation, right? How do metals oxidize, or different metals oxidize? And he said, there were almost as many versions of the phlogiston theory, which is the name of the theory that we're describing this oxidation process, as there were pneumatic chemists. That proliferation of versions of a theory is a very usual sign of crisis. Right? So in Kuhn's reading of the glass field 10 years ago, you would have said, well, this is a field that's in crisis. And you could even argue that it had been in crisis for more than 30 years because that proliferation of theories had been endemic. And what's nice about Kuhn in his book is that he also tells you how you get out of a crisis. Right? It's a very simple recipe. And the recipe is that, well, you just need a paradigm shift. Okay. It's easy. Just change the way you think about the problem and it's all going to go away. Okay, historically, that's quite true. And I would argue that the paradigm shift is happening or has happened. And this is what you have, in a sense, you're super lucky to hear about, because Francesco's lecture is essentially about that paradigm shift. The paradigm shift is the infinite dimensional solution of the phase diagram of hard spheres. And I'll try to argue today how that changes, today and over the lectures, how that changes how we can think about the problem and how we can move forward. So you're at the first row of this major change in human thinking, the resolution of an old crisis in glasses, all the glass problems being unified in ones. And one thing that's really remarkable about this phase diagram, and I'm not going to dwell on this because Francesco will, but for one thing, it does actually unify, it brings to fruition the Liu and Nagel program of unifying jamming in a glass transition, right? Because what you have here is 1 over the pressure, right? So it's like the phase diagram I was showing you before, it's that flipped, right? Infinite pressure is now on this axis here, versus the packing fraction. And you have the liquid here at low packing fractions, and this is the dynamical transition Francesco was talking about this morning. These are equilibrium glasses that Professor Berthier is going to be discussing, has started discussing, and will be discussing the rest of his lectures. And those dashed lines here are state following in the way Professor Zamponi was describing this morning, right? So you take an equilibrium glass state and then you compress it to a different state. And then turns out there's a phase transition, which maybe will be discussed this week. But the thing is that if you go all the way to infinite pressure, you get something that's jammed. It has an amorphous, and these are particles in contact. They carry mechanical force through them. So it's really a realization of that proposal of Liu and Nagel into one unifying description. You could add a third axis that would be shearing. I happen to have no warm feelings for shearing, so I typically don't put it, but it's being done, and it's in some ways done already. So that also is being unified, which is the third axis that Lou and Nagel had. So this proposal, or this result, is really changing, or can really change the way we think about glasses. And one thing that I wanted to highlight is actually the bottom line of those slides. Right? So you may feel that Francesco's lectures go really quickly, that there's really a lot of material. To give him a bit of slack, it took him more than 10 years to work this out. Right? So Francesco and Giorgio Parisi were the sort of two leading people who started this program. A number of people grafted on along the way. Jorge Kurchan, for one thing, who lectured on Monday. I have a very minor contribution, which is the C here. And then Pier Francesco Urbani, Corrado Renone, and Hajime Yoshino are different people who've contributed in different parts. But so it looks all nice and compact, and actually Francesco was writing a book about it, which is going to look nice and compact. But I lived through part of the evolution. I can tell you, it came about slowly and one little step at a time. So this paradigm shift is not a one moment, but it's really a decade of how we're starting to change about glasses and to think about how we can resolve the glass problems. So that's what I wanted to say in guise of intro, right? This is how I think about the problem. It taints heavily my research program and what I'm going to be presenting today. But that's the thing to keep in mind. And it sort of was hinted along the way, and both by Ludovic and by Francesco, is that this picture is very nice, it's very compact, it's very exact, it's very beautiful. Infinite dimensions are not so convenient for experiments, or simulations for that matter. Right? And you may wonder, well, what of this beautiful construction actually exists in finite D? Does it have any relevance to finite D? Is an even cruder question. Some people would say, I'm not even going to listen to this because I work in finite D. I don't have any time to waste with such ideas. Right? But I'm taking the gamble and taking the bet that there is something to be gained out of starting from there. We just need to keep our eyes open to try to make sense of what might be different when you look at finite dimensions rather than this construction. Right? So that's why I would argue it's both important to understand this construction and to understand how it may or may not survive in finite dimension. And this is how ultimately the glass problems are going to be resolved. Okay. So before we get started on the glass problem itself, I thought we'd do a little exercise. You know, I've been told that all of you have taken statistical mechanics at a sort of graduate level. So you already have a profound appreciation of how dimension affects the physics of different systems. So I thought we could start with the simplest system you probably studied in that class, which would be an Ising model without any external magnetic field. Right? Who's heard of this model before? Most? Everyone? Thank you. Okay. So you probably have heard about the infinite dimensional solution to the Ising model. Does anyone know what's a common name for the infinite dimensional solution to the Ising model? It's not the Zamponi-Parisi solution. There's people who came before that who looked at infinite dimension. Francesco, I think you said it. You don't qualify? You didn't take the StatMech class? No. Anyone? I'm a bit. Infinite range? Yeah, but I'm going to take a finite range and take the dimension go to infinity. It's in the similar category of solutions, the same name, actually. Have you heard of Curie-Weiss mean field? Yeah? Okay. Curie. So that's Curie-Weiss. So what changes when you lower dimensions? So I left some blank categories, so I was hoping that you'd provide me with what we should be thinking about. What happens when you go from Curie-Weiss to, say, equals to 1, 3, 4? Yes, this is an interactive lecture. Yes, you sat in the front. Okay, so there's a the technical name for this. There's a lower critical dimension for the transition, sometimes than DL. So you could say D is less than DL, or less or equal to DL. And this would be the case here in 2D. Okay, so this is not true of any of the other. Okay, thank you. Got us started. There's what? There's an upper critical dimension. Okay. So this is, in this case, 1, case 4, right? So this is true of this one, So what's different between? Is he the only one who took this class? A really good institute. So what's different above and below the upper critical? What mean field? What aspect of mean field in particular? What aspect of the mean field solution are going to be valid above the critical exponents? Yeah. Okay. So that's an important one. So here the finite temperature transition disappears. Here you have mean field like critical exponent. Sorry, this one as well. Anything else? I have a cheat sheet here I prepared. I mean, if you want to go into the details, the Curie-Weiss solution predicts a position for the transition. It predicts at what temperature the transition is going to take place. The critical transition times J would be equals to 2 times the dimension for a hypercubic lattice, right? And so the transition location will only be at that position in infinite dimension. Actually, none of the other dimensions would have a transition at that particular. I mean, they have a transition, just not at that temperature. Okay, so it's a fun warm-up. Let's look at using model with a field, right? And one particular version of it, which will be, say I prepare my system. So let's think of it as some sort of Landau-like free energy for the system. It's my magnetization. And so I have a field, I have 2 minima, right? And I prepare my system somehow in this metastable minimum, right? And I tilt the field up until I reach a point where this is flat here. Okay. So what's different in finite dimension versus this infinite dimensional description? And I can ask him again, but anyone else? I mean, I'll have to ask Shri if you don't answer. Does it have an upper critical dimension? Maybe you've not seen this. It does have an upper critical dimension. Actually, this sort of criticality has an upper critical dimension of, so D less than du equals 6. All right, so we say let's D equal 2, D equal 4, D equals 6, D equals infinity, right? So these two would be below the upper critical dimension, and these two would not. Okay. Anything else that happens that's different in finite dimension in this sort of system? Once you hit what's called the spinodal, right? That's the spinodal transition in finite dimension. It's going to be it's going to be a long lecture. Okay, so if I prepare a system this way, in 2D say, you probably have seen movies of this. Prepare a system this way. Right? Typically what you do is that you prepare a low temperature equilibrium state, then you flip the field. Right, how does it typically relax? Okay, please. Oh. There's a jump in magnetization. How does this proceed, this jump in magnetization? Yeah, it does jump. It does relax to this one, right? But how does it happen? Do you have any... Do they all flip at once at the same time? They just get a big party and... Or... Nucleation, thank you. Right? You can design a pathway where there's a small critical nucleus that will form and will propagate in the rest of the system. In what dimensions can you get nucleation? Do you know? Does it happen in 2D? Yeah? Does it happen in 4D? In 6D? When does it stop? Does it ever stop? Is there a finite dimension where it stops? No, it never stops, except in infinite dimension. Right? And we'll talk a bit more about this. Right? So if you're devising a mean field theory of this transition, you have an infinite stability time for those states here that clearly does not capture anything of what's happening in any finite dimension. Right? That's roughly, and then we could dig out small things, but these are the two main things we could have looking at this family of models, right? So there's things that are different in infinite dimension than in finite dimension, or upper and lower critical dimensions, right? The critical exponents changing, right? It's even hard here to talk about critical exponents because there's a nucleation process that competes with the growth of the relaxation time around the spinodal, but you can maybe squint a bit and hope to see critical regimes that's a couple of decades long. There's a lower critical dimension where all the phenomenology disappears, and you can have nucleation, right? And that's roughly what you can have looking at those families of models. Yeah. If you look, that's one last thing I want to say. So these lectures are mostly going to be focusing on the vicinity of that point here in finite dimension. If you want to be looking at a finite dimensional version of Francesco and collaborators' theory, these are the sort of problems you have to face. Crystal nucleation, complex structure, complex activation, upper critical dimension, enucleation process, hopping, facilitation, and potentially others. And essentially what we're going to be talking about in these lectures is going somewhere between the infinite dimension and down to 3 and trying to see what we can say about those different processes. Right? But the key thing is that none of those processes exist in the infinite dimensional solution. And all those processes exist in finite dimension and most likely in 3. We don't really know how important they are. Right? Some of those processes, we have reasonably decent theories that describe them, but we're hard-pressed to say whether that is the dominant feature or in what regime that is the dominant feature. And for some of those processes, we don't even have a good theoretical description. Right? So this is a real... Even if we want a major paradigm shift in how we think about the glass problem, there's a lot of work in trying to go from infinite dimension to 3. So that's what we're going to be talking about, again, as I said. And what we're going to talk about, because one thing you notice that a lot of those effects or you anticipate theoretically, they will become more and more significant at the same time. Right? So you can't tune one and just look at the other by tuning dimension. You can sort of turn all of them on or all of them off by tuning dimension. But that's what we're going to be looking also at a slightly different family of models, known as the Marie Kurchan, that Jorge and his former grad student Romain Marie developed and studied recently. And these actually will allow us to isolate some of those events, isolate some of the processes so that we can maybe better study them. And that's the program, right? We'll see how much of 4.5 hours this covers. So we need to start somewhere. So let's start with the review of things you've seen already a couple of times, and give it a high-dimensional spin. Okay. Crystal nucleation. All right, that's the first thing we want to get rid of. One thing I sort of hid under the carpet set, and Francesco mentioned in passing, so theoretically he can make sure there's no crystal in what he studies by using just a uniform density profile. Right? But if you're dealing with any finite dimensional system, you have to worry, at least at one point, about crystallization. You need to make sure that it doesn't happen in particular. Right? So Don Frenkel was here a few weeks ago. I don't know if he showed those slides, but I think Professor Sciortino showed them yesterday. Right? So what you have here is the same phase diagram I was showing you before. Right? This is a pressure as a function of packing fraction, just different symbols. So this is the liquid branch, the crystal branch, and this is supersaturated liquid branch. And depending on how much supersaturation, so depending on what fluid density, if you want, you started with, you'll get different free energy barriers towards crystallization. Right? And the simplest description of that crystallization process is what's called classical nucleation theory. Oh, and here comes a disclaimer. I have a notoriously horrible handwriting. It's a well-known fact. It's too late. Okay? My mom tried. It failed. Okay? If you can't understand what I write on the board, raise your hand. I will not be mad. I'm very used to it. I'll be happy to rewrite it or to just say it in words louder. So classical nucleation theory. That's what this means. It's not an umlaut at the end. So classical nucleation theory makes a number of assumptions to be able to describe this process. Right? Does anyone know? Who has heard of classical nucleation theory? Right? Okay, so great. So what are basic assumptions for classical nucleation theory? Okay. Okay, sure. That yeah, if we cared about the kinetics of the growth, but yeah, so we could say it's a local process. Transport takes place at the surface, or growth happens at the surface. Anything else? There are rare events. You're in a regime where they're so rare that there's no other crystal around you. So they're, yeah, okay, that's a good, they're independent events. Maybe something, yep. So there's an interfacial free energy, and it's actually the interfacial free energy is independent of orientation and density, for thinking about hard spheres, right? It's some sort of constant number, right? That's roughly. And the fourth one we're going to assume is to assume that the nucleus is pure bulk. It's described by the bulk crystal properties and incompressible. Okay, so these are the four basic assumptions. Yeah, I mean, there's some additional detention actually from the interfacial free energy. It adds an extra compression on but we're not going to care about it. So these are the four assumptions we're going to make. And if we make those assumptions, we can write. Okay, and I should say we're going to do this process at constant temperature and pressure. In which case we can write that the the change in free energy would be the gain in along the transformation will be the change in number of particles in the liquid phase plus the change in number of particles in the crystal phase times their respective chemical potential plus some interfacial free energy plus a surface term, right? And we know that whatever gets added to liquid is subtracted from, what gets added to the crystal is subtracted from the liquid, so there's a minus sign that relates those two. So if I just integrate this, it's very trivially, I can write an sort of Gibbs free energy for the process, which would be the interfacial free energy times the area of a nucleus of radius r, plus the change in chemical potential times the size, the number of particles in that crystal, that nucleus of radius r, right? So I have it here. So that's my little crystal nucleus that I think is spherical. So inside is a crystal, so I have a number of particles in it, and I have some interfacial free energy at the surface. Right, so I can write, I sort of analyze this if I make a few assumptions. So if I set dimensions equal to 3, the area for a given radius is just 4 pi r square. The number of particles in the nucleus would be it's the volume of the sphere times the density, the number density of the crystal, right? And I can plot what this would look like. Delta G as a function of r. It first grows. And so this is your liquid state here. This is a crystal state. If we're metastable with respect to the crystal, and nucleating crystals, the free energy has to be lower. There's a barrier height, so delta G, what's called delta G dagger, or delta G star. Can do the analysis, 16 pi over 3, gamma cube, rho crystal square, delta mu square. Right, but very simple analysis of this process. Okay. I can solve this problem in arbitrary dimension as well. It turns out if I do this in arbitrary dimension, delta G star becomes d times d over 2, gamma to the d over rho crystal d minus 1. Or actually, it scales like it. I'm dropping some constant prefactors, delta mu d minus 1. So one way to restate this, or say this differently, is that the barrier height, so the crystal density is what it is, right? It's a number. If it's small, the nucleation barrier goes up. The difference in chemical potential is something I tune, right? I can supersaturate the liquid solution more or less. So this goes from 0 at coexistence to some large number, right? And this decreases the interfacial free energy. And this is actually what exact qualitatively you've seen. And actually the hard black lines here, the analysis are direct fits to this functional form that Dunn and his student Stefan Auer did 15 years ago. You can do the same thing in 4D, right? We can calculate phase diagram, right? Liquid, crystal, free energy barriers. As you increase the supersaturation, or in this case, the pressure of the liquid, the free energy barrier goes down. Now, what I want to put your attention to, right, and we'll start saying along the way, is that this is really all controlled by gamma. If gamma here, the interfacial free energy, is 0, there's no barrier. Right? All the other terms, I mean, this grows with dimension. This you can tune. This, remains some finite. But gamma, raised to the power d, is really the key microscopic quantity that will tell you whether something will crystallize or not. And because it's so important, I think it's worth spending a couple minutes thinking. Yep. D to the d over 2. Okay. Now, because it's such an important quantity, it's worth thinking about what it means microscopically. Right? The typical context in which you hear about the interfacial free energy is in the Ising model. And you say, well, the Ising model, the interfacial free energy is related to breaking a bond. Right? You've heard this, right? So somehow I break a bond, so this is my cost of having an interface of spin ups next to spin down. So that's a typical scale for that interaction. But here I have hard spheres. I don't have any energy, it's all entropy. Right? So where does this interfacial free energy come from? Well, one way to think about where it comes from is to think about, let's say I have a block of liquid that I will splice in two. Okay, this is my liquid. And then I have a block of solid to which I will do the same. Right? And then I will bring those two halves and put them next to each other. And if those two, so if I keep the pressure constant throughout, then I have two blocks of equal volume that I put together. Right? The interfacial free energy will actually correspond to the increase in volume that the system with a phase coexistence, with a wall of coexistence encounters. Right? So I have two systems that I take them to be of the same volume to begin with. Right? So this is volume V, and I splice them in two, so they're V over 2 in each. And I bring those two halves together, and the net system at the end, at constant pressure, is a tiny bit larger than V. And the way it's a tiny bit larger is because this interfacial free energy corresponds to an amount of PV work I have to do to bring those two systems together, right? There's a net cost. So one way I can write gamma in this context is to say, well, it's the pressure, and I say P is equal to P coexistence pressure, so P coex, times delta, the change in volume that I had from my initial systems to this, my interface. This is my liquid, it's my crystal, divided by the area. Right? So gamma is a trivial dependence on pressure. It scales linearly with the pressure at coexistence, so whatever the coexistence pressure is. And then there's a delta V over A, which so this in 3D this would be a volume and an area. In general, it's a hyperdimensional volume with a 1D-1 area. And this is a length. This is a length in all dimensions. It's how much the fact that I create an interface swells up a bit in this direction compared to my original box. Okay, so if you agree, if you accept this transformation or this reformulation, then if I want to understand what gamma is, what I need to understand is how well a liquid matches to a crystal when I put them together. If they match really, really well, gamma is going to be small. If they match poorly, then gamma is going to be large. And because this controls whether it is possible to nucleate a system of hard spheres, is key to be able to forming a glass. Right? Remember, this is why we're looking at this particular question. Just check. Let me step forward to this one, and then I'll come back to the previous slides. Right, so this is a two-dimensional hard disk system that I have on the left. There are some crystal-looking domains in here, and there's some fluid-like domains in there. Do you think the delta L for the system is large or small? I'm going to look at people to answer questions. Or others. I mean, do I have a good match between the crystal order and the liquid sort of arrangements in 2D? Is that a no? Okay, so let's take a vote then. Okay, so who thinks no? 1 vote, 2, 3. Okay, so they think they don't match well. Okay, so anyone who thinks they match well? Also 3. So 4. Okay, so and it's a class of what, 40? So that's it's about as high as a turnout as a U.S. midterm election. That's dramatic. Equally good results. Actually, they matched really, really well at the surface. It's hard to get a straight line of a crystal in 2D because they mesh so well that the interface immediately starts to meander, which is why if you look in 3D by contrast, right, you have a really sharp interface. And you have, right? You can define. I mean, there's a roughening transition, but it's pretty smooth as an interface compared to what you get in 2D. So if you think about 1D, so okay, yes, what? They match really well. Yeah, they match so well that you can't define interfacial free energy because you can't get 2 phases to coexist. Right? So yes, they blend perfectly. So 2D, so the trend would suggest that it gets matching as you increase dimension, right? At least based on 1, 2, and 3. But we can check 4. So now we can go back to 4. So to be able to see 4, I need to explain to you what the densest packing is in 4D, right? In 3D it was an FC. So this is my cartoon for explaining how you get to a 4-dimensional packing of hard spheres. So and we're going to make a dimensional analogy, right? So if you start with a 2D square lattice packing and you look for the largest gap, right, and you put a particle in that gap, what you get is a rotated by 45 degrees square lattice, right? But you've had to push out the spheres to be able to fit this one in. If you want to do the same thing in 3D, right, you take a cubic lattice and you look for the largest gap, which is in the middle of those 8 spheres, and you still need to push the outer spheres a tiny bit, but less so. Right? Then you get a body-centered cubic as a result. And if you want to do the same thing in 4D, and you take 16 spheres on a hypercube, and you look for the largest gap, which is in the middle, right in the middle of those 16 spheres, and an additional sphere snugs right in. You can put it right along the diagonal. There's no reason to push the neighbors away. And you can see this by, if you look at its coordinates, right? It's half a sphere length in every direction. So the length of this vector is 1. So a half square plus half square plus half square is, square root of. That's 1. So it fits exactly in the diagonal. Right, so that's a perfect lattice in 4D. It's called D4. And the question is, does this match well with what happens in liquid or not? Right? And this will determine whether gamma is small or not and whether we can crystallize or not. It's a bit harder to see. Right? There's different things you can do. One thing that we did at the time when we first looked at this is to look at the ordering of the particles around one particle. Right? So you look at the arrangements of your neighbors, the angles they make with one another. And you define this in a spherically invariant way because your system is spherically invariant. And what we're looking at here is the fluid order in red, in 3, 4, 5, and 6D. And D4 stays in blue here. FCC's in blue here. You can forget the green one, this is just for comparison. D5 is the densest packing in 5D, E6 in 6D. And the key thing to notice is that while in 3D, the liquid order, or what the structures that you can observe in liquid include things that look like a crystal, like spontaneously. They just happen. You're not in a crystal, but there's things that look crystalline locally. If you go to 4, 5, or 6D, there's no hint of such crystals ever appearing. Right? The distribution of structures you get in liquid don't overlap of any significance in 4D, and that whatever overlap might still exist completely gets suppressed as you increase dimension. And so the interfacial free energy, right, which you sort of assume to be related to this sort of argument, or we argued is related to this sort of quantity, should not decrease with dimension. In 4 and 5? So D4 in 4D, as I just described. D5 is the same family as well. E6 is, yeah, you know, I can wave my hands, but it's not going to help you. This is the densest backing that you can form in 4, 5, and 6D. So this is like FCC. Right? It's a different family of geometries, but it's actually, FCC is like D4. It's also what's called a checkerboard lattice. And so is D5. Yep. I mean, but those things are related, right? The interface between a liquid and a crystal is having more and more neighbors, at least half on that plane, having to line up well with a crystal, right? And if it's not of the structures that happen spontaneously in the liquid, it's a constrained one, and therefore you have a free energy cost to pay. And if you don't believe me, you can compute them. Actually, we did it in 4D. We checked the interfacial free energy is about 3 times what it is in 3D. What I wanted to, the other slide I jumped, right? I asked, so in 2D, the mismatch between the liquid and the crystal is so weak that there's actually an intermediate phase transition in between that can develop. It's called a hexatic, where you get the orientational order to form first before you lock in the positional order. And the first transition is what's called weakly first order. So it has a growing correlation length up to some size, and then it gets truncated, and there's a very weak jump in the properties to get them to the hexatic phase, and the second one is continuous. Right? So this very weak interfacial free energy is both a symptom and or it's correlated with the fact that you can go almost continuously from the liquid to the crystal in 2D, with some small caveats. And this is the latest results on the question actually are from Bernard Krauth and his students from 7 years ago now. Okay, so this is the last parenthesis I wanted to solve. I wanted to close on this this question. Okay, so that's our summary for crystallization. Right, 1D is not frustrated. There's no phase transition. 2D is barely frustrated. There are weakly first order and continuous transitions. 3D is somewhat frustrated. Right, you can develop a nice interface. You can supersaturate your hard spheres a bit, but they crystallize really easily, right, if you go too far. The transition is still clearly first order. But if you go to 4 dimensions and up, the crystal just doesn't show up. You can take monodispersed hard spheres, you can supersaturate them, and you're, in that sense, like an infinite dimension. There is a crystal, you can find it, you can calculate its free energy, you can look at its coexistence, but dynamically, it doesn't interfere with your numerical simulations. So, how long would it take? It's a good question. Longer than I can be bothered to wait. Yeah. I mean, there's a free energy barrier. I can show you what it is. So, P27 is pretty close to what we call the dynamical transition. Right, or what you can extract to be, and the barrier is 35 kT. So it's pretty huge, even that scale. You can make it happen if you choose a system small enough that so you break this limit of you have a dilute crystal. If the crystal interacts with itself, you can get it to grow. So that's essentially how you can see it. Or the very densest systems, if they're too small, you can see. So for all intended purposes, we can work in higher dimensions and not have to worry about the crystal. Which even in 3D, you have to worry. Not only do the experimentalists do so, but if you're doing simulations, you're typically not simulating monodispersed hard spheres. You have polydispersed, bidispersed, or whatever family of variants on the system you're looking at. Which makes them ideal in that sense. Though higher dimensional systems makes them ideal to conduct this program of trying to interpolate between 3D and infinite dimension. Well, you're ruining my joke. Yes. You ought to go ahead.
So this is not a question that's formed itself fully, but let me ask you. So, see, even when you're looking at three-dimensional systems, right? When you're thinking about configuration space, you're looking at a very high-dimensional system. So there's sort of some things that some people may have thought about thinking about the phase space, which I guess in this case, it's sort of applying it to real space, right? So is there some going back and forth that's useful to do? Higher dimensional systems versus just configuration
vastness
space.
of configurational space.
Yeah.
Not for me, but maybe for you. I've never given it much thought. I mean, okay, one. No, not in any useful way. But I'd love to hear one if you do. Yeah.
Simple. Like I said, I'm just now one simple thing is like if you try to sort of look at proximal sort of basins or minima. I mean, as you go to higher dimensions, they're all sort of equally far away, right? Which is also something that you have as a
Still is really far away.
No, the neighbors are sort of, you don't have to worry about second neighbor correlations and so on. So that's a similar consideration, I think.
We'll get to that. Oh, yes. Thanks.
Dimensions for even trying hard.
So some in 4, if you try hard in 4, you can. Not in 5 or 6. Okay, so this is my jokes. Those of you who read fast. So I got married recently. The question: if I lived in a 4-dimensional world, could I have bought a nice ring like this one, made with some crystals involved? Maybe we'd all be wearing metallic glasses if we lived in 4D. It'd be a different world of jewelry. Maybe. Okay. Sorry? I'd rather not think about it. Okay, so that was the first column, right? That was the so I'm done with those pages. Okay. So the next column I had in my table. Right, so we've gone rid of the crystallization, but and Francesco mentioned this in this day. So, well, liquids have a structure in finite dimension. In infinite dimension, they don't really, right? Or they have a very trivial structure. But in 2D and 3D, they do. And actually, if you're a chemical physicist, this structure is integral to the way you think about matter. Right? This is from a classic chemistry stat mech textbook by the late David Chandler, where he's looking at the structure of liquids in 2D. Right? So you're looking at how particles are distributed around a central particle here. And you have very, very clear what are called solvation shells. Right? So this is your first solvation shell, and you have a second solvation shell. And these structures are important. You can describe how water solvates hydrocarbons of different sizes based on whether they fit or not neatly within a solvation shell. So this is really important for real-life usage, both in 2D and in 3D, actually. So this is an example. I tried the best I could to find a cross-section of a cluster, but you can see the central particle. There's a first solvation shell, and if you go a bit further, there's a second solvation shell that you can see. And these are very present. Another way in which these have been considered, not just radially, but also orientationally. Right? So in 2D, you will find things that look like 1, 2, 3, 4, 5. This looks like a hexagon, but there's some pentagons as well. There's a bunch of hexagons, some squares in the local order that particles form. Right? And these are all slightly different environments that have. And actually, there's a very nice poster about those local environments. Is it your poster? I saw it yesterday. So we're looking at the tiling on a sphere, particles on a sphere. Oh, Okay, yes. So there's more than one poster where they look at the hexagonal and the heptagonal and pentagonal tilings, and you can enumerate those, and they're very different environment in that context. In 3D, there's a old proposal from the 50s, and it's been revived periodically since, to look at the amount of icosahedral order you could have. Right? As a proxy for liquid order, we now know this is a vast oversimplification. Actually, is mostly not so useful, but people have more careful and more detailed analysis have looked to a variety of different types of local order you can find. This is from Patty Royale's review paper, right? He's enumerated all different polygons you can find, and different models or different liquids will prefer one type of order or another, right, depending on the specific interactions and the specific size ratio of the components. And these actually do play some role in the liquid dynamics, right, and how they solvate some particles and how they self-solvate as well. So these are significant contributions, and none of this is present in the infinite dimensional solution. Right? Francesco made it very clear. There is no such thing as a salvation shell, first. Second thing, there's no correlations between pairs of neighbors around one. Right? All those beautiful polygons, they're completely random. There's nothing preferred or orientationally favored. So how important is this? Right? And well, one thing we can do to try to make sense. Yeah, Shri? Oh. Okay. Ton.
I'm a little confused. So these are looking only at the first coordination shell, which you define with some distance cutoff, or is there something better you can do? But it's distance.
There's as many conventions as there are people who look at this particular question. It could be a distance, it could be a Voronoi tessellation, and that defines your nearest neighbor. It could be...
Okay, and you're just sort of looking at frequencies and doing... But
histograms of
right.
those, yeah.
Is there some sort of understanding of if you go to the second coordination shell, of course, all the structures you have to worry about explode. Mm-hmm. But in some sense, you can sort of see that should be more informative, right? Because
it should be what?
More informative in terms of what organization of particles is happening. But yeah, I mean, I don't know if there's an understanding of whether it's worth the trouble. Yeah.
I mean, actually, I'm not here trying to argue what is the important measure. What I'm trying to say is that there is, positively some order, and some of that order is correlated with difference in dynamics. To what degree, to what exactly order you need to measure? Again, when we talk about myriads of theories or myriads of framework to analyze the same data, this is part of that flora of possible analysis. And the important thing is that if you compare any real dimensional system with the infinite dimensional solution, the infinite dimensional solution knows nothing about this. Right? So if it's important, it's not there. So, to what degree is it important? And is there any way we can recover it? That's something that's part of the challenge. So if we want to look at this, let's say just G of R, the pair correlation function, says G of R is a function of distance for 3, 4, 5, 6, 7, 8 dimensions. And these are hard spheres, but mixtures of hard spheres, so that's why it's not a perfectly sharp peak here on the left. And you can see in 3D, there's a very clear there's a clear first solvation shell and a second one, and then there's even a third one you can see. Actually, if you do this in 2D, you can get a really slow decay of some of those solvation shells to appear. So, in 3D, there's some, and these are pretty dense liquid. In 4D, there's a first solvation shell, and everything tapers down. If you go all the way to 8D, the second solvation shell is almost invisible. Right? And we know that if we went to high enough dimensions, right, in infinity, the solution is like this. This is G of R. This is the theta function that Francesco was showing. 1 being the sphere diameter. It's 0 when they interact, and 1 beyond it. So it's slowly converging to this representation. Right? So somehow this structure, which plays a role, which affects the mean field infinite dimensional predictions, needs to be taken into account if you want to be looking at finite dimension, or if you want to see how important that is, you should be maybe looking as function of dimension. And this is a bit one last quantity. Maybe I can skip it. This is another measure of orientation of neighbors around a central particle as function of dimension and as function of density for different dimensions. So as function of density for different dimensions. 0 here, this is a tessellation, a Voronoi tessellation in all the dimensions. So 0 corresponds to the tessellation of an ideal gas, a perfectly random point process. And the rightmost point here is a model for what the optimal should be. This is a real liquid configuration, but say if you were to pack perfect tetrahedra around a point, there's a maximum number of such tetrahedra you could conceivably put, and this is what this point would be. And any real liquid falls in between the ideal gas and this ideal packing of tetrahedra around a point. And the key message here is that as you increase dimension, even the densest liquid you have look more and more like an ideal gas in terms of structure. So G of R becomes more and more, it still has a first solvation peak, but if you look at the correlations between neighbors, these die out much faster if you go to higher dimensions. So, it's a way to, maybe to approach or to tune this, or to see how important it is, right? If the structure, okay, let's make the following claim. If structure were really, really important, you would expect a big dimensional dependence for the dynamical slowdown of hard sphere liquids, right? That's sort of the suggestion. So we know it has some role, but how significant is it? Well, here's the relaxation time as function of packing fraction renormalized by the phi d, the dynamical transition, or what you extract to be the dynamical transition, as function of dimension for 3, 4, 5, 6, and 8d. And 8d is a smaller dynamical range. Simulations are a bit sluggisher, but what you see is that, okay, there's definitely some differences, but qualitatively they're really remarkably similar. So if there's some role to be played, it's important quantitatively, at least within the dynamical regime that we can access in those simulations, but it's not clear that it plays a significant role qualitatively, or how big of a qualitative role it plays. Right? It suggests that if you start from the infinite dimensional solution, it's not such a bad starting point because a lot of the phenomenology looks like it's not too far away from, in infinite dimension, from 8 to 3, it looks similar looking. So that's the comfort. So you have to care about it. It's going to be important to some degree if you want to be making quantitative predictions, but it's not a bad starting point. Okay, so, yep. Oh, yes, that was... Yes, so actually the slide added this morning because Francesco asked me to. Right, this is 1 over pressure versus the packing fraction. For D goes from 3 to 12. Yes, we did simulations up to 12 dimensions. Okay, and in 3D, and the black line here is if it were only B2. Right, so the equation of state is still pretty far. Right, so there are correlations. They're definitely present. They vanish systematically. If we go from 3 to 12, we're systematically approaching. This is the second variable approximation. It's this black line here. No, because it's all. This is the second variable. It's scaled such that they would all collapse on this one. Okay. So. Yes, they don't. So there's structures, right? So the structure is important. To try to extrapolate where B3. Yeah. Yeah. So yeah, I mean that's a good point. That's where it would disappear. So there's some structure, and we see it in the pair in G of R, and you see it in the equation of state. Sorry. I'm glad you bring this up. So I'm going to tell you how you would do it. So I have 10 minutes left, and I thought, so we'll talk about other processes tomorrow. Today I wanted to talk about so there was no, okay, I thought it was supposed to be a break between, but okay. It was meant to be an interlude. Actually, it was meant to finish on a light note after having talked about crystal nucleation and structure, which are present, right, and or we can to some degree control. The last thing I wanted to talk was a technical one, so how you do simulations in higher dimensions, right? So let me just say 2 words then, if you allow me, and I'll show the pictures for it. So the thing is that doing simulations in higher dimensions, for one thing that I've already mentioned is easier, is that you can get away with monodisperse hard spheres. You don't have to worry about crystallization. So that removes one hurdles of your thinking. One clear downside of doing simulations in higher dimensions is that you need a lot of particles. And the question is how few particles can you get away with? And the general guidelines that you want number to be small enough so that you don't have to run computers for a long time, but not so huge, but not so small that you make it smaller than the relevant correlation lengths in your system, or that you would introduce correlations in your system by having the systems be so small. So from a structural standpoint, we already argued that the structure gets more and more trivial as you increase dimension. So you don't have to have 2 solvation shells in 8D to get good representation or sampling. 1 solvation shell is enough. Right? So from a structural standpoint, that's essentially all there is. From a dynamical standpoint, we're going to discuss a bit the presence of a diverging potential correlation length associated with a critical point. But as you increase dimension, the critical regime gets smaller and smaller. So you can approach the critical point without having a growing length, or it appears later and later in the process. So you can get away a bit from that particular aspect. Another length you might be worrying about is the hydrodynamic length, right? So you have, so if you have a particle that's immersed in a fluid, and you have conservation of momentum, there'll be a backflow. So if it moves this way, there'll be a backflow from the rest of the particles. And this is true also of hard spheres solvated by hard spheres. And this hydrodynamic interactions is long range. It decays like 1 over R in 3D. In general, it decays like 1 over R to the D minus 2. So if you increase dimension, hydrodynamic correlations also decrease. So you can get away with smaller systems. In the end, up to 8 dimensions, you get by with 2,000 to 3,000 particles, and still, avoid correlations that would take place. If you want to go all the way to 12 dimensions, you're more talking about 150,000, 250,000 particles. So at some point, you get caught up. But the key speed up that you get in those simulations is not from. So for those of you simulations might be familiar with this idea of using cells in which you look for one particle, you would look at the 3 to the D cells around it for potential interacting neighbors. So this is a typical construction. In high dimension, this does not help you because the cells, you get essentially 2 on a side or 3 on a side, so you end up looking at all other particles. But if you look at what's called a Verlet list, right? So you keep a list of your nearby neighbors within a spherical shell of where you live. The volume of that shell compared to the volume of the box decreases exponentially quickly with dimension. So you get a speed up by a factor of 1,000 to 10,000 by the time you get 12 dimensions, just from the fact that you're looking only at your nearest neighbors and you're neglecting the ones that are furthest away. So this is how you do it. And with this, I'll stop and we'll get back to it. Oh, yeah. That's it for today. Thank you.